lecture is roughness induced effects and the effects of inertia on the fluid flow through corrugated pipe. These are rather recent results. Šta ako ona ne bude radila? No, it's okay. So this, by this we denote the pressure drop. L is the pipe's length. D is pipe diameter. Rho is fluid's density. And V is the velocity. And of course this parameter here is the so-called friction coefficient. And this is the most important parameter in Darcy-Weisbach law. And our aim is to propose the correction of this friction coefficient by using mathematical tools. And since we were able to do that, we decided to publish this result in the engineering journals. Okay. So our ultimate goal is to propose a correction, a new formula for this friction coefficient, which is the most important parameter in this famous law. Okay, I will now I will not talk about bibliographic literature survey on the pipe flow. You can read it in the paper or in some other literature. I will move to a formal description of our problem. So the problem is the following. Of course, we studied the cylindrical pipe, so the pipe with circular cross-section, which is the most usual one in the applications. And therefore we employ cylindrical coordinates. Why this superindex here? Because we will start from the equations in dimensional form, and then we will write the equation in non-dimensional form. It is if you want to publish something in engineering journal, then you have to work in dimensionless form. Besides that fact, we want to explore the effects of inertia. That means that we want to explore the effects of the magnitude of the Reynolds number on the flow. And that's why we have to perform our analysis on dimensionless equations. Okay, so let us denote by H smooth periodic function with period 1. Which describes the roughness of pipe's wall. And we denote by the absolute roughness parameter. the length of the pipe is denoted by this symbol, and our flow domain is defined as following. So in cylindrical coordinates, we consider a three-dimensional realistic setting. That's always the aim. But when you start to investigate some kind of new problem or the new effects on the known problem, then you always make your primary calculations on a lower dimensional domain, especially if you want to provide some rigorous mathematical results. So the first thing is always to consider a channel. Then if you are successful in that, then you move to a more complex three-dimensional domain, a pipe which can be straight, as in our case, or curved, or with some kind of roughness, or filled with porous medium, or something like that. Okay, this is usual. So essentially, we have a pipe. I have to spare the space on the blackboard. I don't want to erase too much time. So we have a pipe with a rough boundary, and this roughness is described by this function here, h, which is given in advance, and this parameter, which is small. So we have a periodic roughness, because the h is periodic function in the longitudinal direction. This is the classical setting. Okay, so we suppose that our pipe is filled with Newtonian viscous fluid. So the equations written in cylindrical coordinates are the following. Try to squeeze it here. So this is the nonlinear term. Then we have pressure. This is not density, it's a rho. This is okay. Okay, so So 1 over density, the P. This is fluid's viscosity over density. And this is essentially the Laplace. That's the first one. So the nonlinear term. The gradient of the pressure divided by density. And the diffusion term. We assume that the flow is axisymmetric, so we do not have the third component of the momentum equation. This is also standard. We just have a divergence equation. So this is for and the pipe's length here. So we assume that the velocity, and the velocity is given by its components. So this here we have the velocity with two components, the radius one and the longitudinal one. So two unknowns, the velocity with these two components, and the pressure. This is useful to have somewhere written because it is often a standard point in the analysis. Okay, now we have to precise the boundary conditions. And the boundary conditions are usual if we consider the applications. So as you both know, we can prescribe different boundary conditions. In the mathematical literature, when one wants to address some system which is rather complex as it is, then we just put zero no-slip boundary condition on the whole boundary. However, here we want to address a problem which is in line with the applications, and that's why we introduce pressure boundary conditions. In other words, we assume that the flow is governed by the prescribed pressure drop. So the boundary conditions are the following. So we assume the classical no-slip boundary condition on the rough boundary. And we prescribe the pressures on pipes end. And we always assume, in order to fluid to flow, that the right one is smaller than the left one. So we assume here that this P0 is greater than PL. However, in order to Navier-Stokes system to be well posed with regards to pressure boundary condition, here we have to add that the tangential component equals to 0 also. So essentially we consider system 1, 2. These pressures are prescribed. And then one interesting topic is also the issue of existence and uniqueness in case of when you have an Navier-Stokes system equipped with the pressure boundary condition. Then the situation drastically changes compared to situation where we only have the no-slip boundary condition. Because we have the existence and in particular uniqueness of the weak solution only in case of small boundary data. But that's some other topic. Okay, now we want to work in non-dimensional form. In order to do so, we have to have the characteristic velocity. And since we are addressing the pipe flow, the natural choice for characteristic velocity would be a standard Poisson-Hagen velocity, which is computed from here by ignoring the nonlinear terms, and for this shape function equal to 0. So from 1, 2, for h equals to 1, or we just put that the reference parameter equals to 0, we compute the standard Hagen-Poisson velocity. And it reads like this. So it has only one component in the longitudinal direction. Okay, so these are vector. Okay, you understand the notation. So the pressure drop divided by this term here, while the pressure is a linear function. And the characteristic velocity is taken to be the mean value of this Hagen-Poisson velocity characteristic. When we compute, it turns to be like this. So the mean value taken over the cross section, this 2p comes from 0 to 2p, the phi, and it is due to the cylindrical coordinates. This u is this one. Okay, so this is the characteristic velocity. And then we introduce the dimensionless variables. It is also useful to have somewhere this. So first we divide all physical variables by this term here, making it dimensionless. We also divide the pipe's length. The velocity is divided by the characteristic velocity. Here we add the superscript epsilon in order to stress the dependence of the velocity on the small parameter. And we make the pressure dimensionless by putting this. Of course, if you are not sure whether you do this properly, this adimensionalization, then you know what is the unit for pressure, and then you just compute the unit of this and see that it is really a Pascal. So Newton over m squared. Okay, and when you do this, then in the equations naturally appears the Reynolds number. Which is very important for the purpose of our analysis because in the end we are very much interested in the effects of inertia, and this is why this guy here will appear by the nonlinear terms. So we are very, this parameter is, this Reynolds number is very, very important to observe after we obtain our result. Okay, now when we introduce those dimensionless variables and functions, we write this system that I'm just erasing in the non-dimensional form, and this is the starting point of our analysis. So the equations are the following. This we will denote by 3. So Reynolds time the nonlinear term plus the gradient of the pressure and Laplace. The second component and finally the divergence equation. Okay, here we will also write the boundary conditions. Okay, now when we do the adimensionalization, we obtain here the new parameter, and I forgot here to write this parameter epsilon is delta over and this is the small parameter in our problem, which describes the rugosity of the pipes boundary. And boundary conditions. Okay, so this is a vector. On the pipe's lateral boundary. And on the ends, I should also bold this, you understand, okay? And now these pressures are, of course, also made dimensionless using this expression here. And this velocity has two components, the radial one and the longitudinal one. And this is our system that we are going to address. Here we make an additional assumption, which is rather standard. So we take a small parameter to be something like this. And assume that the integral of the shape function that describes the roughness of the pipe's boundary equals to 0, meaning that the parameter epsilon essentially denotes the average roughness of the wall. Okay, so this is the position, the formal description of our problem. I made a brief introduction. I wrote a problem in dimensionless form, and now we proceed to analysis and the main ideas from the analysis. Of course, the analysis is rather technical at some points, but the aim of the lecture is to present the approach and the main ideas. And of course, the next time we will finish this part by commenting on the correction of the Darcy-Weisbach formula. But first, we have to attack this system using the asymptotic analysis with respect to this small parameter epsilon appearing in the problem. So we are particularly interested at the end on the effects of the Reynolds number, on the effect of velocity, and the effects of rough boundary described by this function h. The goal is to compute a higher order approximation for the velocity and then use it in the Darcy-Weisbach law that I just erased in order to obtain analytically the new formula for this friction coefficient. Okay, so the analysis. And it's very interesting when you read engineering papers. They almost always have this structure and these same titles, the titles of the subsections. So introduction, the problem, the analysis, results, and the discussion. It's the usual form of these papers. Okay, so if we have a pipe without roughness, then the solution is in the Poisson form that we computed in order to provide the characteristic velocity. Now we have introduced some roughness on the pipe's boundary, but nevertheless, we still expect that the solution of the velocity for the velocity will remain in some kind of Poisson-like form. So we seek for the solution in the following form. Of course, it's a zero-order approximation. So only one component in the longitudinal direction. So we have the Poisson part, which depends on the radial variable. Excuse me. And we correct it, of course, due to this roughness of the pipe, with some constant. With some constant that will be computed in order to our approximation satisfy this no-slip boundary condition on the rough boundary. For the pressure, we expect that zero-order approximation will remain in a classical linear form. So this constant here going to be computed from the condition 3, 1, 2, 3, 4. However, the rough boundary is corrugated. That means that it depends on the longitudinal variable. So we cannot compute it from this. Okay? But we have to put, so maybe to moderate this, should be computed. Should be computed with this, but impossible. Since it depends the boundary, meaning boundary on the longitudinal variable. So I cannot, in other words, we cannot determine C epsilon such that U epsilon I think it is clear. For that reason, we impose this, that is small. Meaning that this C epsilon now can be computed as plus a term which is of order epsilon. You get it? That means that the velocity takes the following form. And we expand this guy here by starting with the epsilon term. Like this. And this constant will play a very important role in the further analysis. Okay, now, so this here is the correction of the Poisson-Hagen velocity, Hagen-Poisson velocity. And now we use this. We concentrate on the boundary condition and obtain the following. Now I will erase these equations. I will keep this. Okay, so from the no-slip boundary condition on the rough boundary, we have the following expression that will be used in the second. I will write here. So we collect the terms with equal powers of epsilon. Okay, so let us go through this one more time. So it is natural to expect that the solution will be in the Poisson form, but due to the roughness of the pipe's boundary, we correct it with the constant. That constant cannot be computed from the original no-slip boundary condition because it depends on the longitudinal direction. So we start from this assumption that it is small, of order epsilon. That means that it can be computed like this, and that the correction of the Poisson velocity is in this form here. So with some term of order epsilon. Then we expand this term with respect to the powers of epsilon. And then using this form of the velocity, we rewrite the no-slip, the velocity on the pipe's boundary. And now it's idea to use boundary layer analysis, which will capture this, you know? So to build the higher order correctors, the boundary layer correctors, which at each stage will satisfy this boundary condition on the rough boundary. So now we proceed to boundary layer analysis. So this is like so we seek for the boundary layer corrector. In the following form. So our velocity is corrected by the boundary layer correctors, which for the velocity is this one. It depends on the fast variables. So this is for the velocity, and we also write here for the pressure. Okay? Here tau and c are the fast variables. Tau is related to a radial variable, and excuse me, here is radial variable, and c is related to longitudinal variable. So essentially, we will, by plugging this into the Navier-Stokes governing system, we will obtain the equations posed in the following semi-infinite domain. So if you recall what is the range of the radial variable, you conclude that this is for tau, and this is for c. So this is the infinite string. So the idea is, as I said, so this is the corrector, the corrector for the velocity. So we, okay, now I will erase this. So the idea is to substitute the expansion for the velocity, whose zero-order approximation is this one, and which is corrected by the boundary layer correctors, these guys here. And why? In order to satisfy this, okay? Same for the velocity, for the pressure. So we have the linear function that I raised, plus the correctors. Here the corrector starts with order 1. So please denote this here by 4. And the idea is to plug the above expansions into 3, yeah, by taking into account four instead of 3, 4. Okay? Okay, and now comes the rough part. I will not do it all the way because there are many technical details, but I will do the first one maybe, and yeah, that's a lot of technical. It's not for okay, I will just do it for the first one because I have to mention some results that are used, some theoretical results that were obtained before by my collaborator. Maybe to write those references. Okay, so for the first order, for the first order term, we obtain the classical Stokes equation. Posed in the infinite domain. And now, as I said, we have to satisfy this. So, by the term of order epsilon, we put that our first boundary layer corrector satisfy this. And this is the first one with the minus term because we want to cancel this, okay? And also, in order to this problem to be well posed, we have to assume that these are both periodic functions with respect to the longitudinal variable, and that the gradient is in length 2. So this is our problem. Let us denote it by 5. Okay? So we put this into the Navier-Stokes equation. Maybe better we plug the above expression into Navier-Stokes equation by taking into account 4. Then we do not have to write this. Okay. Do you understand this? Here, these are the obvious notation for partial differential equation. Now with respect to fast variables. And now we have some theoretical results which can apply to this kind of systems. in the boundary layers. These are results due to Marušić, Paloka, and Starčević. From Maja Starčević is one of the first PhD students of Marušić, Paloka. It used to work here, but not anymore. Okay, I will erase this. So in their paper published in 2015 in Applicable Analysis, they provided some useful theoretical results regarding this kind of system. So it's Starčević 2015. I think it's applicable analysis. Let me check. Yeah, it's applicable analysis. And that's a good choice for our next paper. It just came to my mind. Okay, so that's proposition 4.2 that guarantees that the problem, due to this result, the problem 5 admits the solution of course, always when you treat boundary layer problems, you have to develop some, to have some kind of exponential decay result. So this one decays to the constant, which decays exponentially with respect to tau, of course, towards a constant. So let it put this formally. There exists constants which we denote like this. So stabilizing constants denoted by the subscript this here, such that that we have the exponential decay towards this constant. Of both velocity and pressure. So this guarantees these results here, this result here. And then, since our boundary layer corrector is divergence free, then we have the result from Edwards in 2019. One of the science journals, I think. It's lemma. I write this on purpose because these are important results that can be useful in the further research. So this is lemma 1 from this paper. Maybe to precise which paper this is, because Edwards tends to publish a lot. So this is, I think, from Yeah, from some journal. Some journal on applied mathematics. And this result guarantees that essentially this stabilizing constant, so these are all at this stage vectors, yeah? Is essentially 0 in one direction. So we have this. For this result, we have this. So this is now not a vector, constant vector, but just a constant. In other words, we have that this component of this constant goes to 0 when tau goes to minus infinity. Okay? And now we have to solve this. And knowing this, we can solve it by introducing the first auxiliary problem. The first auxiliary problem among many. Among many. So I will erase this. So the whole idea is to construct the boundary layer correctors B1, B2, and so on, and to obtain the higher order correction of the velocity. From this velocity, we will extract the characteristic velocity, put it in the Darcy-Weisbach law, and obtain the correction of this friction parameter. That's essentially the idea. So to solve 5, we introduce the auxiliary problem. Which is essentially the Stokes system. And now we want to meet the boundary condition satisfied by V1. For that reason, we put on the rough boundary this. And again, in order to problem to be well posed, we have to have the periodicity in the longitudinal direction. And this as well. We can label this by 6. So this is first of many auxiliary problems. And if you compare this problem with the problem 5, that essentially you observe that it has the same form, and that's why we again can apply this result to conclude that it has the solution which possesses the exponential decay with respect to this fast variable, and that it tends to a constant in this way. So analogously, we conclude that there is a solution which exponentially decay towards a constant only in longitudinal longitudinal direction. However, it is also possible to compute this constant. Moreover, we can compute it by testing this by this function as following. Okay, and now using this auxiliary function defined by this problem, we solve phi, so we solve the problem for the first boundary layer corrector by simply putting that B1, and you can easily verify that, is equal to this expression here. Okay, this K1 appears due to the K1 into in the problem 5, yeah, that I erased. And this is the constant that we can choose. And now the question is how we will choose it. What do we want from the boundary layer correctors? Do we want that it decays towards a constant outside the boundary layer or to exponentially vanish? We want to them to exponentially vanish, to decay towards 0. And this enables us to choose this K1, which appears in our correction for the velocity in a way that this constant equals to 0. And that's the key part. So we choose, I will now this is the last erasing today. Okay, so this is very important. We choose K1 such that this guy here equals to 0, meaning that also the second component of the first boundary layer correctors goes to 0. Okay? And we can put that easily by putting that K1 equals to the stabilizing constant of the auxiliary problem, yeah? Okay, so we conclude that K1 is this. Okay? And now the idea is to continue the computation and construct B2 and I think B3. No, also B4. Okay, B2, B3, and B4. In order to accomplish that, our main tool are those theoretical results, but of course the computation gets more and more complicated because the equations and these boundary conditions are more and more complicated. And for today's lecture, I will stop here. Thank you very much for your attention. You have some questions? If not, we are over for today.